I started looking through my my Mathematica files, and the next one that caught my eye was one entitled Quaternion.nb. NB stands for notebook file. Anyway, the quaternion is kind of interesting as it pertains to the Lorentz transformation and the other rotation transformation, because it is, let's see if I can find the actual description here on Wikipedia. Actually, no, I can't find the exact thing I'm looking for on this thing, but so I'm not entirely sure that what I'm about to describe may just happen to be a particular use of something vaguely related to quaternions. But let me show you a little bit of the mathematics I'm describing. It involves something called Maclaurin Series, specifically the Maclaurin Series expansion of e to the I theta. And you may be familiar with this, that if you do the Maclaurin Series expansion, it comes out to be e to the I theta equals I theta to the 0 power over 0 factorial plus I theta to the first power over 1 factorial plus I theta to the second power plus 2 over 2 factorial plus ... And what happens is this is just 1 plus I theta plus or minus theta squared over 2 plus, or make it minus, I theta cubed over 6. And anyway, all of the I terms come out to be sine theta, and all of the real terms become cosine theta. Now, so in other words, the Maclaurin series expansion of e to the I theta is just cosine theta plus I sine theta. Now, another version of this is, instead of putting an angle up here, theta, you put or rather, instead of putting just the imaginary number I up here, you put numbers in there. So, for instance, you might say you put a matrix, You put 1 and -1, 0, 0. That one's not going to do it quite, but 0, -1, 1, and 0 times theta. And then instead of the I going through, you will just have that matrix going through. Let's fix that. I think it's actually what you want. Hold on. Is something more along this line: e to the power of a matrix consisting of 0, negative theta, theta, and 0. And let's use phi, just so that we make it more distinguishable from that. And go ahead and do the first one of these manually, phi 0, and see what we get. We first multiply this row by this column, which leads us to negative phi squared. Then we multiply this row by this column, which gives us 0. And multiplying this row by this column also gives us 0. And finally, multiplying this row by this column gives us negative phi squared again. So I plug this into Mathematica and need to make one fix. The this times this wait, not that times that. This last column needs to be generated by this and nope. I multiplied the wrong thing in Mathematica. This should be 0, phi and negative phi, 0, right? Is that what I multiplied? 0, negative phi, and positive phi comma 0. That's what I multiplied. So what do I get? Negative phi squared and negative phi squared. That's what I get. Okay, good. So I did get the right answer previously. And if I continue that, multiplying m dot m, m dot m dot m, m dot m dot m dot m, multiplying our matrix through over and over again. Oh, it's not going to fit there. Let's bring it over there. You'll see, well, you'll see that you have that same pattern of negative phi plus 0 plus phi cubed plus 0 minus phi to the 5th plus 0 plus phi to the 7th. So you got that alternating minus, plus, minus, plus in each position. Plus 0, minus, 0, plus, 0, minus. And what you can do with these quaternions is actually, if you define m properly, then e to the m, and I think you can do this without any imaginary numbers in there. You can get an e to the m equals the rotation matrix, cosine theta, negative sine theta, sine theta, cosine theta, and you can also get, if you assign different values to m, you can get the hyperbolic rotation matrix, cos phi, sinh phi, usually negative on both the sinh phis, cos phi. And Mathematica has an ability to do this matrix through the matrix power command. I can just plug in that m, I think, and I need to give it a specific power. Of course, let's give it a power of 3, for instance. And what's it do? Oh, it just gave me the third power of m, the m that I defined earlier. I think actually the command that I'm looking for is matrix exp. So it takes basically it takes the exponent of a particular matrix, and if I basically, oh shoot, all I did was plug in that matrix from earlier, the phi, or 0 phi, negative phi, what is it? There it is. M is 0, negative phi, phi 0, and this gives us the matrix form, the cosine phi, negative sine phi, cosine phi. So here's my code, and you can see that creating this matrix M, which is 0, here it is. No, I didn't. Crap. Okay, as I was saying, this matrix M, which is 0, negative phi, phi 0, 0, negative phi, phi 0, when I take the matrix exponent of that M, I get a rotation matrix, cosine phi, negative sine phi, cosine phi. Now, when I take the matrix exponent of matrix exponent of n, then it gives me this other odd-looking thing. Let's see if we can play with that a little bit and discover what it is. Let me rewrite it as 1 plus e to the 2 phi over 2e to the phi. That's this part right here. And then I will take this part right here and get negative 1 plus e to the 2 phi over 2 e to the phi. And you'll see the bottom two are the same as the top two, but kind of in reverse. This one is equal to this one, and this one is equal to this one. So we really only need to identify what those two things are. Let's start by multiplying this by e to the negative phi over e to the negative phi. So what I'm going to do is multiply e to the negative phi over e to the negative phi. Actually, I'm going to do that with both of them, e to the negative phi. I'm just multiplying by 1, but then I'm going to push those things through, and you'll see e to the negative phi plus e to the 2 phi minus phi is e to the negative phi plus e to the phi. The e to the negative phi, e to the phi cancel out, so I'll just have 2 on the bottom. This one is negative 1 e to the phi is e to the, oh man, negative 1 e to the negative phi. Why did I write? Okay, it's just written wrong. It's negative e to the negative phi plus e to the 2 phi times e to the negative phi. You subtract the exponents and you get e to the phi divided by, and this, oh, there's supposed to be a negative sign there. E to the phi times e to the negative phi is 1, so you get e to the negative phi plus e to the phi over 2. Now, when this one is also the definition of hyperbolic cosine of phi, and this one is the definition of the hyperbolic sine of phi. So what this equation actually gives you is precisely cos phi, negative sinh phi, cos phi is the equation for a hyperbolic rotation. So Mathematica didn't simplify this, but if it had, it would have given us the exact same, would have given us the hyperbolic cosine and hyperbolic sine. And let me make kind of what I think might be sort of a non-scientific statement, but it was this feature of the mathematics that probably has convinced me more than anything else that special relativity is not some made-up arbitrary thing, but it has to do with geometry, so that the hyperbolic rotations in time and that basically acceleration becomes almost perfectly equivalent to rotation. So when mathematically they are, the only difference between acceleration and rotation is the scale, just the difference between the scale of space and time, because basically we seem to be moving incredibly slowly in space and incredibly quickly in time. Essentially 1 second is equivalent to 300,000 kilometers. So that gives you an idea of the scale of these axes. And the other difference is basically essentially in the mathematics, the difference is there's a positive sign here and a negative sign here, and everything else is exactly the same when you compare the concept of acceleration and the concept of rotation.